Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience. Hi everyone, today we have with us Amy Gelmi, who is a group leader at the Royal Melbourne Institute of Technology in Australia. Hi Amy, how are you doing?
Hi, good, thanks.
Wonderful. Let's start by understanding your scientific journey. So how did you end up in your current research field?
Yeah, so I had taken a fairly standard academic pathway, but definitely where I started, I did my undergraduate degree in science, brackets nanotechnology. So I did a lot of chemistry and physics in my undergrad. I actually did my honours thesis on tin oxide nanoparticles for gas sensing many years ago. And so from there, I was looking around to do a PhD. So I did my undergraduate in Perth, which is in Western Australia, and then I moved to Wollongong, which is on the east coast of Australia, to do my PhD with the Intelligent Polymer Research Institute at the University of Wollongong. And so there we kind of focused more on conductive polymers, and I was looking at conductive polymer biomaterials and understanding how they interface with proteins using atomic force microscopy. And that really started my love and soft spot for atomic force microscopy as a research tool. It's my favorite thing. And I always try to squeeze it in. And so now I'm really happy that I get to use it a lot once again at RMIT. So from that PhD, I was working a lot with conductive polymer biomaterials, and then a postdoc opportunity came up in Sweden after, just when I was writing my thesis with Dr. Edwin Jager at Linköping University. And so it was a really interesting project, and it was looking at using conductive polymer biomaterials to design a cardiac patch scaffold to support stem cells and to encourage stem cells to grow into cardiac cells. And so a lot of that project was material design using electrospinning and figuring out a way how to coat the fibers with conductive polymers, and then collaborating with biologists at the hospital to introduce stem cells to these materials and see if we could stimulate them and push them into differentiating or turning into cardiac-like cells. And what I found out with the whole project is tissue engineering is really cool, but we don't really understand what's going on, where these stem cells are interacting with the material, what is happening when we stimulate these cells. And so that kind of prompted me to my next postdoc, which was at Imperial College London with Professor Molly Stevens. So I wrote and felt very lucky to get a Marie Curie individual fellowship to go to Imperial. And so what we were looking at was single cell analysis using atomic force microscopy and Raman spectroscopy to analyze how stem cells might change and respond to external stimulus like electrical stimulus.
Okay.
And so this is going more and more biology as we slide down this very slippery slope, and so we found some really cool stuff during this visit postdoc at Imperial. And so at the end of that, I decided I'd always planned to come back to Australia. And so I'd spent some time applying for different positions and getting a Vice Chancellor's Research Fellowship to set up my own group at RMIT. And so now I'm on kind of using, again, still atomic force microscopy to probe and understand how the cells might be responding to electrical or other external stimulus. But now using advanced manufacturing and nanofabrication to create new kinds of devices to stimulate our cells. And then the idea is that we can kind of hopefully use our devices, use our stimulation to push stem cells to different tissue types, with the goal that we can use external stimulus to target a specific tissue type for an individual patient on a per needs basis. So I've kind of come all the way down now. I'm almost medical, but I'm not quite there yet. So I'm still in the lab, still working in a chemistry lab.
Mm-hmm.
Hopefully staying more on that side of it, just collaborating a lot with clinicians and the medical people as I need further down the line.
Mm-hmm. Okay. Wonderful. That's a very, very interesting journey you've had, and you've traveled around the world. It's like a typical scientific career. I feel that you start somewhere in a continent, and then you move. You do several postdocs, and then you become a group leader. That's fantastic. And it's an interesting journey. So you already did touch upon what you are currently doing, or where does it fall in this big picture of the materials or nanoscience. But if you have to summarize it, like just in a few sentences, so where does your current research as a group leader now, where does that fall in this big puzzle of materials and nanoscience?
Yes, I think definitely on the nano side is my use of atomic force microscopy. It's actually, people might be more familiar with it as a materials uh, characterization device, but it's really, really useful in biology as well because we can use it to measure and interact with living cells, actually grow our cells on our substrates where we're providing the simulation, stimulate them and do AFM at the same time because we don't need to fix our cells or do any of the more conventional biology with it. And so we're measuring nanoforces, looking at changes in the membrane topography, being indentation. And so there's a lot of single cell kind of analysis that we get out of AFM. There's a lot of information down on the nanoscale that you would translate up to kind of this broad tissue engineering area, but it's down on that scale that we can really start to understand how the stem cells are responding.
Mm-hmm. So when you say stem cells, what kind of cells are these? As a material scientist, I'm asking you this naive question because during my PhD, I worked with neurons, which are brain cells, and cardiomyocytes, which are heart cells. So which cells are you looking at with the
So,
AFM?
yeah, so specifically, I work with human mesenchymal stem cells. So
What is
these are so these are stem cells that actually we can isolate from the bone marrow. And so the reason why I really like working with our mesenchymal stem cells is one, they grow pretty flat, which is great for AFM. And they also can turn into or differentiate into cartilage cells, bone cells, fat cells, smooth muscle cells, nerve cells. So they're quite pluripotent, so that means they can turn into quite a few different cell types.
Okay.
And I like them as well in a broader position because you can get these from adults. So I have commercially obtained donor stem cells from 3 different donors. So a patient could still come in and we can get human mesenchymal stem cells from their bone marrow, but you can also get it from fat tissue and also from dental pulp. So it's a really good source of adult stem cells, and it doesn't have all the ethical issues that embryonic stem cells can come with as well.
Uh-huh. That's interesting. So it sounds to me that I mean AFM on living cells, that's already kind of magical is the word I like to use, because it's really fascinating. So it sounds to me that you do a lot of interesting experiments in the lab. So if you have to pick one, which was the fun or quirky or like, so you had the most fun or fun doing, could you pick that experiment out and explain it to us in the section we call In Other Words?
Yeah, so there's definitely one that comes to mind. So it wasn't him, but it was with another, might be common to some of the materials people with ramen. So
Mm-hmm.
we were trying to measure the Raman spectra of our living stem cells,
Mm-hmm.
measure intracellular molecular changes, because that might tell us a little bit again of how the stem cell might be responding to our stimulus.
Mm-hmm.
My the material that we deliver the stimulus through is a black biomaterial,
Okay.
and we need a fairly strong laser to get enough of a signal from the Raman laser from our cells. So we need to put quite a high power up on it.
Mm-hmm.
So we normally worked on tissue culture plates or glass when we had it on this black material. What we found was that after using our 5 or 10 second measurement, we had completely obliterated uh, the single cell that we were trying to measure Death Star style. So it was just, we even saw like a slight flash of light in the petri dish. And so what happened was, due to the heat caused by the laser it was focusing on our cell, with this black polymer below, it just completely obliterated the cell and left a crater in its place. And that was the day that we learned that we probably weren't going to manage to get Raman spectra on our stem cells. We did kill a lot of single stem cells single-handedly, one laser spot at a time. It was a very good learning experience. Probably not great for the stem cells, but it left a big imprint on me.
That's fun. That's fun. Hopefully, you can talk more about it on the Twitter account and explain how exactly did the Death Star kind of explosion happen with the laser. That's wonderful. Great. So I hope that your research so far has been fantastic. However, if you would want to improve it, and if you had 3 wishes to improve it, what would you ask for? And I'm not promising anything here.
I guess one thing that comes to mind that I wish if I walked in the lab tomorrow I had, and this is I could actually get it. I should probably just order it and go ahead. But if anyone has any tips on this, it would be great. I'd really like a barcoding system for my lab. So for labeling samples, labeling cells, labeling chemicals, and then integrating that into an electronic lab book would be fantastic, because my handwriting is terrible, and trying to read what I've written on tiny cryo vials that are really small and they go into liquid nitrogen for months at a time, and then I've got to fish it out and try to read what I'd written is really annoying. So if I could get a barcoding system up and running, that would be great. And I think I just need to go ahead and bite the bullet and pick one. But I'm just which way to go with that. I think, and then thinking retrospectively, when I was like in my PhD, I wish I'd gotten more advice before taking my first postdoc on. Not that I didn't enjoy my first postdoc, but I didn't really feel like I had a good grasp on what I could do or where I could go. So I kind of jumped on the first opportunity, which did work out for me. But retrospectively, I'm like, oh, I wish someone had sat me down and given me a little bit of career advice and thought about it that way. So I always try to do that now when I talk to PhDs who are finishing up on new postdocs. I try to chat with them and to see, what do you really want to do? What are you interested in? Where do you want to go? See if I can't help where I feel like I maybe missed out a little bit there. And if we go back even further, back to my undergraduate days,
right?
I wish I'd done more coding. I see it's so common now, and so many students are fantastic, and they just can whip anything they want up in MATLAB or other kind of software. And I wish that coding had been a bigger thing in a science degree when I was an undergraduate. And so I've tried to learn, but I've already learned so much. I already learned biology and all manufacturing, and it's just like my brain, I can't take another field on right now. So I collaborate and I work with some really fantastic like computer engineers and scientists and bioinformatics people, but I wish I'd learned more about that. And I think that would have really helped. And I think that's another thing I always encourage students. I'm like, learn some coding, learn how to do at least some basic stuff so that you can write your own analysis software and write your own code up to solve the problems that might be unique to your research. Because it's really annoying when you're trying to like Google and find out if anyone else has written a module for ImageJ.
Well, yeah.
Please learn that and then join my lab because I need you.
That's great. All 3 wishes super, super important, and I completely relate to that. And the first one, as you said, you can already get it by yourself, and the other 2, you're already doing it for the next generation of researchers. So that's fantastic. Even if I can't grant you the wishes, you're already making them happen. So that's wonderful. So let's talk a bit about the future. So the next 3 months. What are you looking forward to most in the next 3 months?
I'm really excited because we found out in November last year I got a really big research grant. So I have an ARC discovery project, grant here in Australia. It's 3 years. I'm the lead CI on it, which is crazy to me, but here I am with another fantastic co-CI with me who's in engineering, Kate Fox. She's brilliant. So I've got a new PhD student starting hopefully soon, and a second one coming mid-year. So he's not going to reach that 3 months, but so I'm just really excited to start getting this PhD student onto the project, and the honours students as well that I've got starting, getting them into this project. I'm just can't wait to get cracking on it because I think it's going to be really great, and it's like my first big project, my first big funded research project. So I'm super keen, and then I'm also heading to World Biomaterials Congress in Glasgow in May. So that's three. Yeah, so I'm really excited about going off to Europe and meeting up with friends and meeting new people and chatting about my research there.
That's wonderful. That's congratulations on the grant, and wish you good luck with the conference, with getting the PhD students, and starting up your group leader related activities. Now, before we let you go, what we want to understand from you, or what we want to hear from you, is what are the challenges or the big questions that the research, like nano or material science field, is facing at the moment? Because it's very multidisciplinary, so the challenges are slightly different, I guess. So, what are the challenges? And you are working at the interface of natural and life sciences. So, what are the challenges here?
Yeah, so I think one of the challenges is when you're working at that kind of interface is making sure that you're getting input from both sides, because I've been really lucky, like especially when I was at Imperial and during my PhD as well, I worked in really multidisciplinary groups. And I think so much to benefit from that, that when you have chemists and biologists and engineers all working side by side, you get a lot of different perspectives on how to solve a problem. Like, I really feel like biologists are probably like, what is she doing, when they see kind of the way that I try to solve biology problems. But sometimes I get kind of like crazy, weird results that end up being super interesting because I'm taking a non-conventional approach.
Mm-hmm.
And I think that a lot of challenges, especially in the areas of biomaterials and nanomedicine, like you really need that multidisciplinary and diverse team if you're trying to solve those problems, because if you get too many people with the same background and training, you're not going to get that fresh look at what you're trying to solve. And so, what's the point? You should have kind of lots of different perspectives and ideas, and you might get a fantastic idea from a chemist who maybe knows a lot about lipid membranes as a biologist, and vice versa. Your biologist might turn around and say, "Hey, did you think about checking out this pathway in the cell, because that could be a big reason as to why this is or isn't working." So I think I challenge people to be more diverse when they're building their research groups, if they're doing disciplinary research, of course.
Mm-hmm.
Or maybe even if not, you never know. You get some crazy ideas from people outside your field, so it's always worth chatting and
Okay, yeah, that makes sense. So embrace diversity at all levels, in all walks of life, and in the lab, so in everywhere.
everyone.
Face it.
You just
Okay.
need different opinions on everything.
Absolutely. Wonderful. It has been lovely speaking with you, Amy, and we look forward to having you on Real Scientist Nano.
Thank you. I'm looking really forward to taking it over and tweeting my heart out.
Wonderful. Thank you for listening. To know more about us, please visit our website, realscientistsnano.org, and follow us on Twitter at realsci_nano.